So, we've been talking about, well, from the beginning, right? We had regular languages. So for regular languages, we had a DFA, an NFA, or a regular expression that we could use to describe those. We saw then that the determinism and non-determinism didn't affect what you could do with the machine, just how you did it. So there were theoretical uses in one version or the other, things that we could tell. Application-wise, any language that could be recognized by a DFA can be recognized by an NFA. So the non-determinism, the probabilistic aspect, didn't change anything. For context-free languages, from the machine perspective, we had push-down automata, and then we had context-free grammars. And in this case, it does turn out that some things require non-determinism in the PDA. So for the PDA that we created for palindromes, in the PDA for palindromes, we had in the middle of it a lambda transition where we guessed where the halfway mark was. We went through reading characters, putting them onto the stack, and then at the halfway mark, we said, okay, let's start popping. And so palindromes, as far as the PDA is concerned, requires that guess in the middle. So context-free languages, some of them require, for the PDA, some require the non-determinism and some don't. So it doesn't change the fact that of the language being context-free because there's still a grammar for it, but the PDA itself sometimes can require that non-deterministic aspect. Okay, then we talked about things like some languages that we showed were not context-free, like we looked at a language like this and saw that it was not context-free, but we saw that if we had a PDA with two stacks, then this problem, or this language, is recognizable. We can determine, is this string in this language or not, with two stacks. And then we talked about if we even did something like this. This language, again, is not context-free, but with two stacks, we could still take care of it. And we could even go on as long as we want, and we never needed more than two stacks to deal with things like this. Okay, but what we didn't answer was, would we ever need more than two stacks, right? Are there languages that might require more than two stacks? All right, so what we're going to do now is we're going to talk about a new type of machine for our purposes. We're going to talk about a Turing machine. So a Turing machine is, again, building on what we have so far, but rather than having a single stack, what we have is an infinite tape. And each cell on the tape can hold a single character. And then we have a reader or a tape head that can move left or right. It can read what's in the cell, and it can also write new things in the cell. All right, so it can read or write. And it also then has a finite set of states for memory. Just like a DFA has a finite set of states for memory, a Turing machine has a finite set of states for memory. Now, what we will have then is an alphabet for the tape and an input alphabet. They may or may not be the same thing. So we're going to, again, typically be talking about binary input, so strings, and then writing things to the tape that might be, again, exactly the same alphabet or maybe some extra possibilities. An empty cell, again, on the tape, we will represent with our triangle for the same way we did with stacks. So if you had absolutely nothing at all on the tape, every cell would have this symbol. Otherwise, what we're going to think of with our Turing machine is once we've created it, described the language, described the states that correspond to everything, and so on, then we will have our input on the tape. And the reader or the head will start at the leftmost value. So when we turn it on, that's where it will be. So if we had input, this input would be in here. And then we're going to process that input and do whatever we need to do with that input. Okay, so excuse me. We can do things like describe what the head is doing by things like this. We might have a state and then say, okay, for instance, we might say, if we read a 0, let's write a 0 and then move the head to 1 unit to the right. So this is the kind of description that we'll have in our machine. Right? So this would say, read a 0, write a 0, move 1 unit to the right, whatever, right? So that would read this 0 and just take it out, look at it, and write a 0 right back. You could do other things too. You could write a 1 and then move. So sometimes we allow left or right, or we, in certain situations, will allow the machine, the head to stay put. So sometimes we would have left, right, or stay. So different variations on the machine, but the original idea was to move left or right and then read or write. So Turing machines were created, or the theoretical groundwork was laid in the 1930s by Post and by Turing. And so, again, these developments happened before actual computers were ever built. And so they determined what you can and cannot compute before we had ever built any computers, at least electronic computers in the way we think of. But their ideas determined kind of the design of what happened. So let's think about a language that we've dealt with before. Obviously, every regular language, I don't know if it's obviously, every regular language can be recognized by a Turing machine. In what way? Well, for the Turing machine, you can put the input on the tape of the language, and then not really worry about it, just read things and move to the right, and then follow the steps in the automaton. Right? So if we had a DFA down here, let's say, we're just getting our input from there. We never really said before where we were getting the input from with a string. We said, oh, you have this input, do this, do this, do this. Where are we getting it from in this context? We could just say, well, get it from the tape. Have the automaton do whatever it needs to do. Okay, so what we want to explore is, can we mimic a stack with a tape? Can we mimic 2 stacks with a tape? What about 3 stacks or 4 stacks? So we'll talk about all of this as we go. But let's just take a look at a language. Let's look at this language that we've considered quite a bit now, that is not that is context-free, but is not regular. So how would you recognize a a string in this language. If I asked you to, I'm going to give you a string, and I want you to tell whether this string is in this language. And remember, we can't really count things because we don't have a place to store that. But what would you do to tell if that string is in the language? And remember, this is so all of this is on the tape. One's character per cell, and we are sitting right here, right now.
So what sort of things are we able to keep track of?
You're allowed to
read, write, stay,
move left,
Can you
or
keep
right.
track of how many times you've read?
No.
Or right?
This is all we can do.
It's all we can do.
And we have a finite set of states that we can move through, but it's a fixed finite set. So it can't be, we can't have states that say, okay, well, if you're in this state, that means the first time, the second time, the third time, and so on, right? Same kind of limitations that we had before. So what would you do if you wanted to tell whether this string is in that language? Now we can tell, but again, because we can count, so we can just count the zeros and count the ones, but we can't do that with this machine in this situation right now. So what would you do to be able to take this input and determine whether...
Can you keep track of how many times you move left and right?
We don't have any... You can keep track up to a certain, like a fixed number, because that's how many, you have finite set of states for memory, so you can keep track up to a fixed value, but then if your string was longer than that, you wouldn't be able to keep track. You can keep track of it if you've moved an even number of times or an odd number of times, that kind of thing. But we can't keep track of actually how many times because we don't have the extra space for that. Where we are right now. I mean, we can add features and so on and see if that improves things. But so what would you do?
Thinking through some solutions, just kind of spitballing. I know these aren't the correct answers. One approach, I guess, would be read through the string from left to right, and replace all the zeros with ones, and then do the reverse, and then replace the ones with zeros, and then so you basically flip flop and then go back.
So if you flip flop and went back, then we would have ones followed by zeros, but we still wouldn't know how many of them, right? And our question is, do we have the same number of them?
Yeah.
So let's take that idea, right? What are we allowed to do now? We're allowed to do something more than we were allowed to do before. Before, once you used a symbol, you couldn't go back to it.
No.
But now we're able to move back and forth. You can compare things, you can look at things, and so on. So let's take a look at this 0. And we say, okay, what do we need to do with this 0? In order to tell whether the number of zeros is the same as number of ones, we're going to need to match this 0 with a 1 somewhere.
Yeah.
Right? We need to match this 0 with a 1. So what could we do? We could turn this 0 into this symbol. And then do what? Then start moving to the right until we get where?
A 1.
The first one?
I would say, yeah, because then...
Okay, so let's see what happens. If we get to this first one, now you're say, turn it off. That causes a problem, right?
Yeah.
What problem does that cause? When we run into this symbol, we think that maybe there's nothing else after it, or maybe there is, we don't know.
So you go until the last possible...
So what if instead, what happens if we go...
I think you can click the eraser off the... Or no, like, click it into empty space first, and then drag it up and... I guess not. I think it's just, because it registers it based on size.
Yeah.
So like if the object's big enough, it'll register as an eraser.
Oh well. So what happens if we go until we get to that symbol. And then do what?
Move back one.
Then move back one,
Replace that.
check to see if it's a 1. If it is, replace it.
Yep.
Does that make sense? So we start at the 0 at the beginning, check to see, is it a 0? If it's not, what can we do? We just stop right then, right? It's not in the language. But then, if it is a 0, we're going to replace it with the empty cell symbol. Then move to the right. Read zeros, read ones, all the way until we read the empty cell symbol at the far right. Move back 1, replace that with an empty. So now what have we done? We've been able to replace the 0 at the beginning and the 0, and the 1 at the end. So we know that those match. Then what can we do?
Go all the way back.
We can go all the way back to read that delta. Move 1 to the right.
Switch it out.
Replace that one. Come all the way to the end until we read this delta. Come back 1. Switch it out. And we can keep doing that. Back and forth until what? If the string was in the language,
Then
they would all be marked off at the right time. If the string is not in the language, there would either be
one left over.
1s left or 0s left. Right? Either too many 1s or too many 0s. So what would happen if there were more 0s? You've read a 0, you move to the right, you read the delta, you come back and you try to replace a 1, but there's a 0 there instead. And otherwise, if there are too many 1s, you've wiped off the 0s and your first symbol, instead of being a 0, is now a 1. Does that make sense? So we could move back and forth. Start at the left, move all the way to the right, come back to the left, all the way to the right, left, right, left, until it comes down to things matching or not. Can we improve on that any? Can we speed that up a bit? Can we speed that up just a little bit? What if, once we mark off this 0, we come over here and mark off this 1, instead of coming all the way back,
We just go to the next one.
go to the next one,
Grab
mark
that.
it off,
then
and
go
come back and try to find a 0 to match it with. And then find a 0, match it with a 1, find a 1, match it with a 0. And what would that do? That would cut down the number of times we go back and forth. It cut it in half, right?
Yeah.
Because we're not coming all the way back and then starting over. We're working from both ends toward the middle.
So that theoretically makes the process 50% faster.
Okay, so roughly 50% faster. Taking care of things, right, in half as many steps. In some sense. I mean, we can be more specific about exactly what's happening. But yeah, right, cuts it in half, because we are not just working from one end, coming all the way back and working again and again. It's working toward the middle. All right, so is this particular string in the language? Right, we would work through, and I didn't count when I was drawing them. I just drew a bunch of 0s and 1s. And so I don't know, is 10? Okay, it is. So what happens in that case, as we go through this process, we would end up with, on our last 0, we would go to the right and read a 1. And when we come back, there are no 0s to be read, and we accept. Okay, so we want to describe what a Turing machine for this looks like. In one hand, this is a description, right? A written description, write out the words for it, is sometimes the way we describe a Turing machine in paragraph form. But let's see if we can describe this idea in our state scenario. So what do? In the start state, if we read a 0, we do what? right there, we write the delta, and we move to the right.
If we read a 1.
Well, so that was taking care of that very first position.
Yeah.
Now what happens? From here all the way to here, what do we do?
Read a 0, keep going.
Right?
Right.
So we read a 0, write a 0, and keep on going.
Do you have to write each time?
Yeah.
Okay.
I mean, the idea is you
So you
because
have
you
to
kind of
write
taken
the
it out,
first
you have to put it back if you,
Okay.
right? So that's
Because it only removes to look at.
Right.
Because it can only see after it takes
right.
out.
So it takes it out, looks at it, puts it back.
Okay.
What else happens on this? What if you read a 1? What do you want to do?
Keep reading until you get to.
Right? If you read a 1, you write a 1, and you keep going to the right. Right? So we have two things that happen there. We can put it on a separate loop or the same, right? It's these two possibilities. All right, so now what? If you read a delta, what do?
You write a delta and move to the left 1.
Write a delta and move to the left. So that puts us right here, right now.
Yep.
So what do you do at that stage?
Read a 1. Write a delta. And then you move to the right. Or no, you move to the
Now
left.
we're moving to the left, right?
Yep.
Okay, and at this point, we're sitting right here.
Yep.
This is now a delta. This is a delta on this end. And we can decide, do we go all the way back to the beginning, or do we now alternate and start moving? But this is the setup of how the Turing machine might look in diagram form. Okay, so let's say we decide to turn this into the delta and work back. What do? We read that one, wrote a delta. Now we're sitting here. So what are we going to do? Actually, we have to be more careful.
Yeah, I don't think we loop.
We don't want to
there.
loop on that.
It's almost as if the width of that just isn't big enough.
Yeah.
Or it's very particular about the way you have to put it down.
So what happened? So now what are we doing? Let's see. We were
You
here.
write a 1.
Wrote the delta, move back to the left.
Then we
read a
read a 1,
1.
write a delta, move to left.
Now we're sitting here.
Yeah, now we're sitting there.
And
Read a 1, write a 1, move to the left.
let's see. At this point, let's write this right now as the complete going back to the beginning, right? So move it all the way back to the beginning and start over. So what have we done? We replaced this one. We came over here. We read this delta. Wrote the delta. Moved back to the 1. Read the 1. Wrote the delta. Now we're sitting here.
Yep. So now you want to read. If you read a 1, you want to write a 1.
And move to the left.
Yep. And then if you could read a 0, write a 0, move to the left. That's
Okay.
all the way back. And then if you read a delta,
Read a delta. But it's going to be this delta.
yep, you write
We're
a
going to
delta.
write a delta
Move to the right 1.
and move to the right 1. Right? And that puts us back at the beginning, which where is this state really?
That's currently at a 0.
So what state is this one really? This state is really
That one. Once
that
again.
state,
Yep.
right? So this is really not a new state. This one is really,
Back to the start.
take us back to there.
Yep.
Do this again, do this again, do this again. Okay,
And that would mean
but now we have to have an accept possibility, right?
Yeah.
And so what are we looking at? When will this accept?
I would say on the start state here.
So what happens in this case, we have a separate state. When you come down to the accept portion, we will have a state, and it will come from wherever it needs to come from. And it will say, okay, if you have, so we have whatever state we're, say, okay, if you've read the right thing, what's going to happen? If you've read a delta and there's only a delta, whatever, then maybe we stay. and then there's an accept state. So what happens, well, we'll finish this off, but when we write down an accept state, the Turing machine is like a PDA. Once it goes to the accept state, it's there, right? That's the end, it stops, and it accepts. It's like a PDA when we had drawn it with the flowchart idea. Once you read the right pieces, you went to the accept state, the machine said accept, and you stop. So what's the idea here? The idea is as we move back and forth, we are, in this particular case, marking off the matching pieces, and if they end up matching, then we are going to accept, and if they end up not matching, we're going to not accept. Okay, so we want to give you a chance to work with this and try to finish this off and see what you think. So let's think through the idea of palindromes. How would you deal with a palindrome in this case? How would you tell whether or not something is a palindrome?
You would do the same similar process and match the letters to the letters.
All right, so this time you're going through the same you could do this in a similar way, but instead of looking for the other character, you're looking for the same character, right? So whatever you read here is what you want to read there. But we would have to keep track of that a little bit, right? How do you keep track of which character you've already read? So I'm going to give you some time to work on this, and we'll think about this as well. Right? So then we'll come back and compare answers. But you kind of get the idea of what's happening here, right? What do we still need to do? We still need to work our way to the end and figure out from which of these states, or if there are new states that are necessary that will lead us to the accept, what happens when things are good, and what does that look like? So what's the idea of a Turing machine from this perspective? This feels a lot more like writing programs the way we normally would. Right? This feels a lot more like being able to read things, write things, move back and forth, right? Instead of before, we were streaming everything, and as you used a symbol, it's gone, right? You can't come back to it unless you had some way of remembering, you had enough states to remember something about it, you can't get the exact thing back anymore. But here, what can we do? You can go back and forth, either be able to overwrite things, you can change them, or you can keep them and come back to it and look at it again later if needs be. Okay, so let's experiment a little bit, and let's try to finish off a Turing machine description in this format for this language, and then let's see if we can do the same kind of thing for a palindrome.